Start, Madhura.
Okay, sir. So I'm audible?
Yes, you are.
Okay. So hello everyone, I'm Madhura and I'm with the Alumni Relations Cell. So I'd like to extend a very warm welcome to everyone who could join us today. With us today, we have Professor Somnath Roy, who will be talking about building real estate in the nano world. Now, Professor Roy had completed both his MSc and BSc in physics from the Banaras Hindu University, followed by which he completed his PhD from IIT Delhi in 2005. He was also a postdoctoral researcher at the Materials Research Institute of Pennsylvania State University in 2006. Currently, he is a professor at IIT Madras and is working on the growth and study of 1D nanostructures for solar energy and gas sensing applications. And he has also been selected for various accolades, one of which is the Bhaskara Advanced Solar Energy Fellowship and also the Shastri Indo-Canadian Institute's Faculty Travel and Internationalization Award. Now, before I hand over the session to Prof. Roy, I'd like to request everyone to type their questions in the YouTube live chat box during the session, and I'll be reading them out after Prof. Roy's talk. So over to you now, Prof. Roy.
Thank you. Good evening, good afternoon or good morning, depending on wherever you are. Thanks a lot, Madhura, for this nice introduction. Also, thanks to the Alumni Association. So today I'm going to talk about some of our research work here at IIT Madras in my lab at Department of Physics. So let me share the screen. Is it visible, Madhura?
Yes, sir, it's visible.
Okay, yeah, thank you. So when I got invitation for this talk, I was thinking how to make sense of what we are doing. Of course, as you will see in next about half an hour or 45 minutes, things are, for some, things may look pretty abstract, things which you cannot even see. First thing is called seeing is believing. Of course, you cannot see, when I say you cannot see with naked eye. Of course, we have a host of electron microscopes with which we see regularly the things that we make in nano world. And I thought, well, real estate, something, I mean, everyone wants to own a piece of real estate. And here real estate, particularly, I mean the buildings. So I thought, okay, the nanostructures that we make in our research, I'll call them the real estates in a nano world. So I'm in the Department of Physics. I'm an associate professor in the Department of Physics, IIT Madras. So the outline of the presentation, roughly, I'll follow this. I'll give you the background and motivation, what motivates us, and how did we start all these things. Then broadly, 3 technical things where we made the nanostructures. What are these nanostructures? How we made them? StIO2 graphene oxide nanostructured composite, then copper oxide nanoflakes, and Cu2O heterostructures. And the third one will be the vertically oriented bismuth ferrite nanorods. I'll also briefly give you some glimpse of very fundamental work recently we have done to measure the electrical properties of single nanostructure, that is one single nanostructure, where we are looking at in my research or at globally, and then the acknowledgements. So of course, Madhura is introduced, but just for everybody's convenience, I wanted to flash this slide for a minute. I was born and brought up in Jamshedpur, did my schooling. Jamshedpur, now it's in Jharkhand. That time it was in Bihar. Of course, then I went to BHU Varanasi to do my graduation and master's in physics, followed by IIT Delhi. I had a brief stint in the Amity School of Engineering, Noida, that's near Delhi. And then I went to the Pennsylvania State University for my postdoctoral research, spent about 4 years there. And since then, from 2010, I'm here in the Department of Physics, IIT Madras. So nano, you must have all heard now. It is no more a new thing. It has been there even before it was formally discovered. by a couple of discoveries, Nobel-winning discoveries in the 80s and 90s. But then it was there. Of course, it is around us. So just to give you a perspective of what length scale we talk about the nanomaterial. Of course, this is one particular schematic I have taken up from this paper, which is shown here. So what we see around us, let's say you talk about sand, a dust particle that's, let's say, start at 1 millimeter, pollen 100 micrometer. 100 micrometer is also typically the width of our hair. Well, I have lost many, but it is our standard human hair. Red blood cells, bacteria, virus. Oh my God. So everybody is talking about virus, coronavirus and all. So this typically around from a few micron to about 100 nanometer, fraction of a micron, like that. And then we have the proteins, the protein molecule, large molecule that is around 10 nanometer. You come to DNA strands around 2 nanometer. You have the Buckminster-Fullerene C60 and then atom 0.1 nanometer. Of course, we can go down to electron and then the subatomic particles. We are not going to discuss so much about those things. So typically in our research, we work on the length scale here from about a nanometer to about a micrometer, around 100 to 10 nanometer, particularly here. Now, the question is then, what happens if you make a material at that dimensions? What happens? So two particular things that happens at that dimension. One is higher surface to volume ratio. Second is the electronic property change due to quantum confinement. Quickly, I'm showing a very simple example of what do you mean by higher surface to volume ratio. You may please ignore the units here. Of course, the units will be volume unit and then surface unit. Let's say, let's consider you take a Rubik cube, standard Rubik cube, 3 by 3 these cubes. So if you consider the sides of 1 unit, then you have 3 units, the small cube of 1 unit side length, then you have sides, 3 sides. So surface is 3 square into 654 and the volume will be 27. So if you consider surface to volume ratio, just the numerical ratio is 2. And if you come to a smaller medium size cube, 2 by 2, you come at a surface to volume ratio of 3. You can see that calculation. Of course, I didn't make these graphics. This I have taken from internet. Now you come to further smaller. There is the smallest cube there, and you get a surface to volume ratio of 6. So this is a simple example of how the specific surface area, what we call the relative ratio between surface to volume, actually increases when you go from bulk, our everyday sizes, everyday around us, what we see around us, to the nanoscale. Now, how does it matter? It matters. It matters means any phenomena, any property, anything, any application, including or involving materials. Well, all applications around us is involving material, right? Whether it's a solid, gas, liquid, that's a different. So material here, particularly, we are talking about solid materials particularly. So any material where you are looking at a property that is surface sensitive or dependent on surface, right? So that is going to change. That's going to be enhanced when you come to in a nanoscale. Second most important thing is that quantum confinement. Of course, quantum confinement itself is a topic of, multiple lectures we take in the course of quantum mechanics. However, here I'll just give you a very day-to-day example of quantum confinement. So generally, I'm sure many of you have heard about that, depending on what your background is, of course. But then for the sake of everybody, I'm talking about this here. So now we have confined the material to nanoscale. Let's say a very small dimension. Suppose the material is confined so much that the electrons inside cannot move freely. Well, right? So simple example is you have a big room, you are sitting comfortably. For example, I'm now sitting comfortably in front of my laptop. Suppose somehow hypothetically the walls come closer, so closer that they almost encompass me, around me. That means the dimension of the enclosure becomes almost similar to the dimension of myself. Or in other words, the electron's de Broglie wavelength, okay, similar to the space where the electrons are confined. So it's like what we say normally, if we are confined in a closed space, that I'm feeling suffocated and all that. That means my behavior, my normal behavior, my comfortable behavior will change under confinement. The same thing happens to the electrons. So their behavior markedly change under confinement when we reduce the dimension of the solids to that. Okay. And that actually gives rise to whole lot of new properties. Okay. And then, so these two are the main thing that actually manifests themselves in all the nanomaterial. And there are a host of properties that changes, but on the most fundamental scale, this is the surface to volume ratio and the electronic property change due to quantum confinement are the two most fundamental and significant properties. Here I come to now coming to do justice with the title of this talk, today's talk, that is focus or theme of the research, the real estate in nano world. Well, I have shown some picture of tall buildings, very famous building. Of course, the left one, you know, is the Petronas Towers in Malaysia. This is in Singapore, one hotel, and this is another building called, I think, called hashtag building in Seoul, South Korea. So let me, before going there, let me read the first paragraph, what I have written here, the first bullet point. One-dimensional metal oxide nanostructures direct growth from an underlying substrate in array form with vertical orientation. This is our core interest in our research. It doesn't mean that we don't do other things with this. So, as you see from these buildings, these are high-rise buildings, and high-rise buildings are vertical, all vertical buildings from a level ground, right? So consider that we are able to make our nanomaterials vertically up from a support called a substrate. This substrate can be a metal substrate, can be a glass substrate, depending on the kind of applications we are looking at. So this is one of our focus area, that we make the nanostructures. Let's say this is the pen I show. If the hand is the support, so I make it in this. This is what I wanted to mean as the real estate or the buildings in a nano world, that we all make vertical nanostructures. Why? Why we are interested in vertical nanostructures? First thing is that, well, you can make any type of nanomaterial. You can make any type of nanostructure, whatever way you want. It is not the only way to make nanomaterial. And you can make it in powder form or other things, and then you can coat it. But then if I can make the nanostructures directly from a substrate, then I have much more flexibility in terms of directly making into some devices or some other applications. Okay, this is one thing. So that is one thing I wanted to highlight through these buildings, the picture of these buildings. Second, one of the main applications that we are looking at photoelectrochemical water splitting and gas sensing. I will not particularly highlight this, since our the theme of today's talk is more into growing the nanostructures, not as much as applications I can give. Some later on we can talk about that. But I'll just explain this application, that photoelectrochemical water splitting is simply where we want to extract hydrogen from water. As you know, hydrogen is has the highest calorific value. And hydrogen is the clean fuel. Now the question is, we have water everywhere. Well, I can take hydrogen from water, but how? Water is extremely stable, you know, otherwise we would not leave. So how to take how to take hydrogen from water? Now, obviously there are electrolysis process, but then if we consider about, doing it in a sustainable manner, then you have to use renewable energy. What renewable energy you can think of? There comes sunlight. There is abundance of sunlight, abundance of water. But then it appears that again, sunlight cannot just shine on the water and can break it. If that is the case, then the oceans will just vaporize, right? So it is not that. So here lies the principle of photocatalysis, that there are material which absorb sunlight, then they produce electron hole pairs. Bit of physics or chemistry is here, but don't worry, we'll not discuss that much. And then they actually break through oxidation and reduction reactions. I'll show it in the next slide, to make hydrogen and oxygen. Oxygen, anyway, you can leave wherever you want. Hydrogen, you can run a lot of things you can do with hydrogen. You can run a fuel cell, produce electricity. Good thing is that in this ideal, a dreamy cycle, energy cycle, that it again fuel cell produces water which can go back. So this is our motivating concept. We can we can make hydrogen using sunlight through photoelectrolysis of water. Why I'm calling electrolysis, I will come shortly to that. Not pure photolysis. Well, photoelectrolysis, we need a little bit of electric field, and we can produce hydrogen. So this concept that we can produce hydrogen from water was given by a phenomenal paper in 1972 by Fujishima and Honda. It's one of the highest cited paper in material science, about 40,000 citations. So this is where just a bit of looks like some chemical reactions. Don't worry. SC is the semiconductor which shines light and produces electron hole pair. So in the right, as you can see, simple valence band band picture from a solid state physics book. That is, I have in a solid valence band and conduction band. When you shine light, the electrons from the valence band go to the conduction band. Holes, that is the vacancies in the valence band, which actually ionizes water, and then the H+ ion transfers through this electrolytic cell on the other side, where you have the electrons, and the electrons are actually producing from the conduction band, and then here H+, and then here the H+ actually combines with the electron to give you hydrogen. As such, the entire thing is done in 3 reactions only, but it's not so simple. So what you need actually, you need this semiconductor which can efficiently actually absorb sunlight and then produce the electron hole. Here lies the challenge. So far, we have not found a single component semiconductor, a single material as a semiconductor, as an ideal semiconductor, which will absorb sunlight, the large portion of the sunlight, and which will, make this happen. So our research is around this theme of developing this semiconducting material that will help in producing hydrogen from water using sunlight. So just some technical stuffs here, that what we want, if you want to use sunlight, obviously then you want the major portion of the solar spectra to be absorbed. So when we talk about sunlight, it has about 4 to 5% UV, about 45% visible, and then IR. In principle, you want to have your material so that it can absorb the entire sunlight. We are not too much interested in IR, the entire IR, because then IR has its own heating effect, which can degrade material. Of course, there are materials which can efficiently absorb IR, but even if you can absorb 40 to 50% of the entire solar spectra, that is from the UV to visible, that's good enough. That's good enough. So then the second is fast charge separation and conduction, low loss. So since I talked about that, you need that electrons to jump from the valence band to the conduction band. And the beauty of this concept is you need both electron and vacancy. So I need to separate them pretty quickly. Otherwise, the electron will jump back to the valence band, which is called recombination, and it is lost. So we have to do something that the electron and hole are separated. So this is the same problem as we face in solar cells. Then you should have appropriate valence and conduction band position. So here also it is important, depending on what kind of redox, that is reduction and oxidation reactions you are looking at. It could be water splitting, it could be other chemical reactions also. You should have a proper position of your conduction band so that you can get the electron from that level. You should have a proper position of the valence band so that you can get the hole at a desired energy or the vacancy. So here lies the additional challenge, that not only this gap is important, but where this edge lies and where this edge lies are also important. Obviously, you want a material which is non-corrosive, non-toxic, and then it's stable, high surface to volume ratio for faster reaction. Mind it again. When we talk about water splitting reactions, means my material will be surrounded by water. So that means again coming back to the role of surface. As much as surface area I will have, more water will be able to catalytically react with the material. So the bottom line is tailoring a material at the nanoscale with respect to both microstructure and electronic properties hold the key to success. Coming to now one-dimensional nanostructures. As I say, consider this pen, and let's say this pen is my nanostructure, and you shine light on this. What will happen? That as I said, electron hole pairs will be generated, right? Now, then the thing is that this kind of one-dimensional nanostructure has already the property of nano, which is high surface area. Now, if you consider the electrons are generated inside, so the electrons can flow only in one direction. There is not much scattering here and there. Regular porosity, I will show what I mean by that. Orientation and aligned morphology. So this is one thing that we want all our nanostructures in a particular orientation. We do not want a randomness, too much of randomness in the whole. So nanostructures directly grown on a substrate in a thin film form, in a coating form. What you will see in your naked eye is a coating. But when you see under microscope, you will see the nanostructures. Then vertical orientation, as I said, vertical orientation is something that we are looking at, not like randomly lying horizontally on a substrate, but they are all grown vertically, and the applications. The first topic, as I said, there is titanium dioxide. Now, titanium oxide or titanium dioxide, TiO2, is around us everywhere. You believe it or not, it's around us. We use talcum powder. I have this paint in the wall around me, and the talcum powder, the sunscreen paste or lotions everywhere, there will be significant amount of titanium dioxide. Titanium dioxide is a white material, powder type material. Advantage is that it is chemically and thermally stable, then corrosion resistance, and it has, I'm not going through the technical jargons here, long hole diffusion length and all, but it has a very good property of sunlight absorption. Now, coming to that, we are particularly interested in, as I said, one-dimensional. In this, we are able to make nanotube architecture, as I will show here. First, I will show here what do I mean by nanotube architecture. You see here, these are all small nanotubes. As you can see the scale here, these are all about 1 micrometer, that is 1 into 10 to the power minus 6 meter in length. The diameter is still smaller, about fraction of a micrometer or few hundred nanometers. So these are all made in an aligned form, as you can see. These are electron microscope images. So these kind of structures that we are dealing with on a day-to-day basis. So how do I make them? As you can see, one of the easiest way to make these nanotubes. You have a beaker, you take some electrolyte. Let's not discuss with what this electrolyte are. This is some acidic electrolyte, okay? If you have a question, we can, discuss those technical things, later. But then simply a beaker, it's simple beaker chemistry. I take a beaker, I have a platinum foil, which is a cathode. Then simply a DC power supply. Why we prefer a platinum? Of course, it sounds too costly process. Of course, once you take a platinum foil, it lasts for years and years, probably many years. It doesn't happen anything. Nothing happens. We want to make titanium dioxide nanotube. So what we do is that, what is our source of titanium dioxide? Is here we take a titanium metal foil that we use as the anode in our electrochemical process. You have a voltage supply which can give you a voltage of anything. We start from 5 to 100 volt. You can go depending on what is the length and what is the diameter you want. We can run this process from 30 minutes to about multiple days, 3 days, to get very long nanotube. You have to treat it thermally. You have to give a heat treatment after this process is over in an oxygen flow. Of course, even if normal air has a lot of oxygen, it does. And then we can get the nanotubes with diameter 10 to 100 nanometer, and it can go to length, of, in principle, if you can think, it can, the entire thickness of the titanium foil can be anodized. In fact, there are papers here who have shown that the entire foil, if you can run the anodization process very delicately and under a strict observation, the entire thickness of the metal foil can be made into the nanotubular structure. So it all depends on what we want. Again, coming back to this, we can make the nanotubes of different morphologies and of different diameter, different length. This is what the beauty of this process. Okay, now as we see that, although you are seeing the aligned structure, we have taken the image from different angles to show you. But if I can see, if this is my foil, let's say I have shown my mobile phone, if this is my titanium foil, then all these grow like this. As you can see, all these grow almost perfectly vertical. This is the beauty of the things. Now I'll come to this point that I have made a building. Okay, all these are, let's say, vertical structure. I want to make the building more functional. I want to make these buildings more useful. As I had shown the pictures of this Petronas Tower connected by a corridor in between, then that hotel in Singapore, there is a top, there is a, roof type thing, but which connects all the buildings together. What people achieve by connecting this? They have more functionality, more convenience, more user friendly. Okay, so this is that. So we have decided to connect these nanotubes together with graphene. And graphene, all of you have heard. I'll not go into the details of graphene. So we started this work when I joined, shortly after I joined in IIT Madras in 2010-11. And luckily, I was also joined by one of the very, my colleague, Dr. Manu Jaiswal. That time he also joined. And we actually teamed up. And my second graduate student, PhD student, actually took up this work, TiO2 graphene composite nanotubes. So before that, we tried to look up whether people have done this. There were, of course, some attempts to wrap the individual nanotubes with graphene or graphene oxide layers. But they had failed because the point was that the earlier generation nanotubes were all very compact, very, very compact. So all it happened that whether they call it reduced graphene oxide, since this is not a pure graphene carbon only, there are some oxygen or other functional groups. So it is called, the reduced graphene oxide. So they are all, the sheets were all confined to the top of the nanotube, as you can see here, as you can see here, as you can see here, top of the nanotube. We said, no, it's not going to work. So what we did was, I will first show here, then I'll come back to that point. We changed the chemistry of the anodization a little bit. We had some hint from a previous paper, and we changed the chemistry of that. And we got these beautifully separated nanostructures, which are no more very compact. Now we had plenty of space in between the nanotubes. And in doing that, we also got a strange morphology that we got multi-leg nanotube, but that is not primary focus here. But as you can see, each nanotube, which are grown from the titanium foil, are well separated. So when they are well separated, we found this thing structure here. Then we had to run two different techniques. One is called photo deposition. In photo deposition, what did we do? We actually procured commercially available graphene oxide precursor, and then we dipped our nanotube material and we shine light. Of course, this is not from our experiment. Yeah, this was from a paper in 2008, but I'm just showing it what they did. The first time they did photo deposition, they worked in powder, TiO2 powder. The other approach that we took was, we again took those TiO2 nanotubes grown on titanium foil, and we used this as an electrode again. And then we put this graphene oxide here as an electrolyte. And again, we did electrochemical deposition. What happened that the graphene oxide, the layers of graphene oxide actually covered and wrapped around the nanotubes so beautifully, as you can see here. I'm sure you can all see. Of course, this is not much contrast here, but as you can see here, we got beautiful structure as if that someone has gift wrapped our TiO2 nanotube. As you can see, this fine, almost thin, almost transparent layers of reduced graphene oxide, which are actually wrapping around and connecting, joining the tubes. Okay, this is one of the most beautiful things. Of course, I can always call my things beautiful, but beauty lies in the eyes of the beholder. But then, of course, I'm sure many of you agree that it's nicely wrapped. So here, that is one of the first real estate business in the nano world that we did, our nano world. And we measured the photoelectrochemical properties. I'm not going into the details of that. Of course, I can respond to queries later. I mean, even through email later on. So, and we found a substantial increase in the light harvesting and the current generating capabilities of this TiO2 nanotube with the help of this reduced graphene oxide. So mind it, I would like to here say specifically that we are not calling them graphene, these sheets or these thin layers, because they are not only carbon layer. They are all carbon layer with some functional group attached, which is called reduced graphene oxide. So this is one of the most beautiful work that we have been able to do. And then I'll not take time here too much, but just to emphasize the fact that since, again, this is much of fundamental research, we needed to understand how these materials behave under AC electric field, under DC electric field, under light, all that. So we did the impedance measurements and we found out various different parameters here. I'll just go through this here. But one particular work that I would like to mention here, this we did in collaboration with CSIR IIP Dehradun. So that time we did not have the facilities and they were kind enough to extend their facilities to us. So this was that we all know global warming, carbon dioxide and all. We can't do much about it. Of course, one way is to reduce carbon dioxide back to hydrocarbons or some value-added chemicals. Again, the question is, how do I reduce? We need energy to do that. Where from the energy come? Well, solar energy, again, our favorite thing, look up the sky. Well, don't look at sun directly. So, which is called CO2 photo reduction. We use this TiO2 graphene oxide wrapped TiO2 nanotube for CO2 photo reduction. And we found that CO2 is actually converted into carbon monoxide and the other chemicals under light. So we did this experiment, like we have a chamber in which we keep our material, our real estate in the nanoscale. Then we pump in carbon dioxide, a small chamber, and from top we have an opening, a glass opening window where we shine light, and then we actually sample out the gas at regular intervals, and we found that CO2 is gradually, reducing from CO2 to other chemicals. So this paper has been nicely cited in last 2 years. Second real estate, if I can say, I'll talk about copper oxide nanoflakes. So I'll quickly come here first, and then I'll tell the background of the story. You know copper, you all know copper. It's another ubiquitous material around us everywhere, electrical wires, and then the AC tubes, everywhere we have copper. Now, another problem with copper is that you leave copper in air, you don't have to do anything. You leave it here, you know that it will form an oxide layer, which for iron we call rust. For copper oxide, blackish, brownish layer will form. That shiny thing will go off. Okay, you just leave it, it will form. Now the point is that copper oxide, CO, when it forms, it is again a good material for solar energy harvesting. It has a band gap of around 1.5, 1.6 electron volt, which means that it can absorb UV, visible, and part of the infrared radiation as well. As you know, silicon has a band gap of 1.1 electron volt, which is widely used in solar cell. Copper oxide has a band gap of 1.5, 1.6 electron. Point is, when you want to make copper oxide in nano form, again, our interest, nano form, you can hardly get pure copper oxide. What happens? Whatever we looked up at the literature, and when we try to do that, whatever you try to do, unless you are very, very careful, you can get this nice single needle type nanostructure. But if you are not careful, you will always land up with a mixed phase of CuO and Cu2, cuprous oxide and cupric oxide. Why? Because always the oxidation is not complete, and then you have an insufficient oxidation somewhere in these structures, growing structures, which results in a mixed phase. So this is my fourth graduate student, Subis John, who actually wonderfully came up with some chemical approaches, and he created through multiple steps. I'm not going to details of these steps. They are available in papers also, I can share later on, but for the sake of time and to keep the discussion around the growth. So he has actually created this multiple step process. And what he has done is that he has created pure single crystalline, I'll show you here. As you can see here, pure single crystal and pure phase copper oxide nanoflakes. There are no trace of any Cu2. So this work was also very nicely received in the scientific community. Now the question is that, again, we ran the water splitting experiments to see if there is an increase in the current under light. Yes, we found an increase. And of course, there are collaborative effort. We have sent these samples for different application to different groups. Our collaborators who are checking supercapacitor application, lithium-ion battery applications for that, the things are still going on. So now coming to the more interesting part. I'll skip these technical details here, but here I'll come. Now, we again revisited, as I said, we did not want CO2. But now again, see, scientists are very selfish. They sometimes say, I don't want this material, but after some time they, oh, no, this material is good. So I am like that. We thought of something else. Okay, what about making a heterostructure? In a common terms, a heterostructure is, one example is a PN junction. You can take a PN. So two different material in PN junction, of course, you have silicon. Here, that can happen with two different materials also. It can happen that if you, so the heterostructures or the heterojunctions are simply the combination of two materials. When you join them together, in such a way, you have to think about the design of where the holes will go and where the electrons will go. So the efficient heterostructures are like those where I can take electrons from the one side to the other, and I can take holes from the other side to this. So what heterostructure does vis-a-vis a single structure is that it can separate the photo-generated electron-hole pairs more efficiently. So here we found an interesting thing that if copper oxide, cuprous oxide and cupric oxide heterostructure is made, it actually forms a type 2 heterostructure. Type 2 heterostructure is, as you can see here, the conduction band and valence band is of one material is higher than the respective conduction and valence band of the other material. So what happens? The electrons go this way and the holes go this way. But we found that this had been attempted in layer form, thin film form. We thought, no, we are the nano guys. We have to do it in a different way. We are the real estate guys, vertical guys. So we had to do it in a different way. We revisited the old problem with a completely new perspective. So here we first made CO2 nano. Mind it, again, we are being selfish. Now we have ditched. We had ditched CO2. We are coming back to CO2. We just did again controlled oxidation, but we did not allow CuO complete oxidation to go. We stopped it at Cu2O so that little less oxygen. Normally CuO means your copper and oxygen are 1:1. Here oxygen is less, as you can see here. Then we did another round of treatment in an hydrothermal vessel. And as you can see here again, beautifully, as like we are stretching the hand, is the center one, or as you can call it, a stem branch architecture. We can see the center one here is this Cu2O, and from Cu2O, it's like I'm stretching my hand. From Cu2O, the body, the nano flakes of CuO, which you had seen earlier, these nano flakes have grown. How did we grow that? Even like all great discoveries, it's a mystery. We found it accidentally, but then we actually ran it very systematically. We found that we have given some model here. We are trying to now understand more why it happens exactly. But then this is somewhere we have to succumb to nature, right? We are succumbing to nature many ways. Here also, there is a point beyond which we don't understand as of now. So we are saying, of course, this is how nature is. Nature is so beautiful that it creates such structures for us. All we have to do is to put the right ingredient, the right temperature, the right ambience at some vessel, and the nature will do it. Well, we are trying to understand this. More, but this is another beautiful work that we have done. That we have produced this, or I can call it also cactus type. My student did not like this word cactus. That this Cu2O. So where I have this center portion is Cu2O, and the flakes which are coming perpendicularly are actually CuO. Again, we have found that the current generated photocurrent under light, electrochemical photocurrent, had 1 order of magnitude increase when we had this kind of structure. So we ran every possible scenario. I will tell you, we found that, of course, Cu2O, CuO helps, but we wanted to check, is that this flex, this nanoscale 3-dimensional structures are helping anyway? For that, we skipped the step of this flake formation. we just had a simple thermal processing where over CO2O, as you can see the top left, we had done a coating of CO, simply a coating, no flat type, needle type structure. Here also you find, and we found an increase in current, but it is like only double, 2 times increase, not a 10 times. So which mean that if I coming to this, all that we did, so what meant that in this nanoscale, in this kind of structure, it is both CO2O, CO heterostructure that is helping, as well as this kind of nanoscale branches from this vertical structure, basic structure, these nanoscale branches, they are helping. So here is one of the most beautiful example of how surface area enhancement is actually helping in enhanced solar energy harvesting. Compared to if you look at this second structure here, there is not much enhancement in surface area. But if you look here, these all branches actually enhances the surface area a lot. So this work was published last year, and quite a few groups are actually interested in this work, and we are sharing our materials, and again, like they are exploring many things. So the last and final thing I'll talk about, I'm well within the time, I guess. Yeah. So the last and final thing I'm going to talk about, vertically aligned bismuth ferrite nanorod. This work is still in progress. I will share with you the excitement of this thing, why we are excited about this, but then a lot of things to be done. This has not still reached its potential, but I'll tell you what we have done. So bismuth ferrite, as you can read here, the chemical formula, BiFeO3. This is a very special compound. This has got ferroelectric property, ferromagnetic property, and then photovoltaic property, meaning it has a very good ferroelectric and piezoelectric property in one, and then ferromagnetic property, which is called multiferroic property. And also it has a band gap, optical band gap of around 2.4, 2.5 electron volt, which means that it can absorb up to till about yellow-green light in the solar spectrum. So the interest in this material was there, but then after in about 2009, around 2009, one group from Berkeley showed that they can make very good solar cells out of this material, because the ferroelectric properties actually enhance the internal electric field, and which can actually separate the photogenerated charges much better than in silicon. So a lot of interest has grown in this material. Why we got interested? Again, our real estate business. We look for vertically aligned structures. When we looked up the development around this material, we found that a lot of work were reported. But everybody had done either flat film, fundamental studies related to single crystals, or nanoparticles. We thought, why can't we make vertically oriented nanorod or nanostructures on this? Okay, so I will just briefly, I will tell you here what did we do. That we took first simple iron hydroxide, FeOH solution. Sorry, we started with iron chloride solution. We dipped in, just immersed glass, specially conductive glass, FTO coated glass. When we do that, we don't have to do anything. It is not our work. This part was already reported, where you can see, beautifully grow vertically aligned FeOOH nano. This is a metastable structure. What we did was, our innovation was that we put it in a coating chamber and we coated it with thin bismuth metal, bismuth layer or bismuth particle, very thin bismuth particle. So it becomes bismuth coated FeOH. Then we did a very controlled thermal processing, and then we found bismuth ferrite nano. Again, one of the most beautiful work we did. Well, of course, you may say, what's so big deal? You just did a couple of things, which part of the thing was already known, true, but then this was not attempted before. And then even doing what I have shown in a few diagrams took about 1.5 years for my 5th PhD student to do. And so with this, this is the scanning electron microscope pictures. As you can see here, I'm showing here, as you can see here, this nanorod, the top view, and as you can see here, the cross-section view. So this work is still in progress, because the phase purity. As I said, when I want to use some material for some technological application, you want the material in a pure phase. As I mentioned, the copper oxide pure phase. This problem with this bismuth ferrite is still we don't have a very clear or very pure phase of bismuth ferrite. There's still a mixture of bismuth ferrite, and there is another phase of bismuth ferrite. But of course, in a single rod, the majority of the phase is bismuth ferrite. So we have done X-ray diffraction analysis, we have done transmission electron microscopy and scanning electron microscopy to actually prove that the majority of most of the length of the rod, a single rod, had BiFeO3. But then we also detected the phases of BiFe409, which is actually an impurity phase in the whole picture. So the properties, when we measured, the properties, we did not get a very high values vis-a-vis the form of material that already been reported. So we are still working on that, but I wanted to share this excitement here. As you can see here, this butterfly loop, which is a signature of ferroelectricity. So we have actually shown this butterfly loop, and we have shown that yes, ferroelectricity exists. We have also shown the magnetic properties. Yes, ferromagnetism or the magnetism also exists, which actually confirms that we got these nanostructures of bismuth ferrite, single nanorod or the nanorod arrays of bismuth ferrite, vertically grown from the glass substrate. But a lot of more work is going on. To wrap up today's presentation, I will now show you very interesting thing which has happened in last 1.5 years. In fact, during the pandemic time, we actually had the results, and then we compiled them and we published them recently. See, I have shown you a lot of pictures of these nanotubes, nanorods and all. We had a lot of time we spent last couple of years, we spent on growing these exciting nanostructures for several applications. Some few applications we are exploring on our own. I did not show everything. And few other applications we are collaborating with with people inside IIT and outside IIT. We wanted to look at how a single nanotube or single nanowire behaves. So we had carried out the charge transport characteristics on single, as you can see here, one single nanotube here, which is actually placed onto photolithographically patterned electrode. And we have also done a detailed modeling of that, empirical modeling of that. And we have also shown that till what current it sustains and then it breaks, what voltage it sustains and it breaks. So that if someone is interested in future to make a single TiO2 nanotube device, he or she will have the idea from our work that what kind of nanotube can sustain what voltage limit or the compliance limit or the current limit. So this work is on a more fundamental scale, but very interesting work we have done. Similarly, we have taken up these copper oxide nanowires also, and we have done similar measurements, and we have seen here another particular thing that I will show you. We have done the diameter dependent charge transport, that we have actually taken this copper oxide nanowires of different diameters, and then we measured the current voltage characteristics, and we found that there is a markedly different behavior. Of course, here also, as I said, there is a role played by the impurity phase. If what you see is CuO, there are traces of Cu2O inside, which actually also affects the charge transport characteristics. So we have shown this, that how these kind of things are there, and if you want wires of a particular conductivity, of a particular current compliance or a voltage regulation, then what kind of wire you can use? What is the what kind of diameter of nanowire you can use? So this just to give you the things. I think yeah, it's about 50 minutes. So I think well within the time. So I would like to wrap up. We are doing now a lot of this fundamental work also, along with our our real estate development, real estate business going on. We are engaged in doing new things. Obviously, every scientist, everybody does like that. Nothing new, nothing unique. But then we are looking at more exciting structures. One of the things that has recently come into the material science community is quantum materials. these quantum materials are the materials where the electron spin play a very significant role. So we are trying to see that if our material, which are in a nanoscale single crystal material that can be exploited for some of these quantum phenomena, strongly correlated systems, we are trying to see that is something our near future goal. And several other things we are trying to make nanoscale PN junctions and heterostructure I have already shown, but those heterostructures were not PN junction. We are trying to see that if one of these, let's say TiO2 nanotube and graphene wrapped around, let's say TiO2 nanotube is an N-type material. Now, if I can make graphene layer as a P-type, then I have a nanoscale PN junction, nanoscale diode. What I can do a lot of things with that and the nanoscale. So those are the things we are now exploring. Of course, with our collaborators, we have in our department, our collaborators, with them, Dr. Ranjit Nanda is there, with whom we are doing a lot of DFT modeling, and we are trying to understand the theoretical aspect of this whole thing. How do they behave? What is the theoretical understanding? How much we can actually achieve practically? But on a more global scale, I would like to highlight, for a general audience, I would like to highlight that the more we have achieved in nanomaterial over past 30, 35, 40 years, nanotoxicity is one thing which we need to actually look at in a more detail now with the global healthcare crisis and all these virus things are there. But always there are these, when we make materials in the nanoscale, there is always chance that they can enter into the human body much easily. For example, when we put talcum powder or anything, any cream, they have very fine, I mean, almost like not exactly nanoparticle, but in that, and they actually penetrates little inside the skin through the pores, but they do not create any problem, any harm, because they are all, have a very, very low toxicity, and they all are biocompatible or at least skin compatible. Okay, so this kind of, investigations need to be done as we explore new kind of nanomaterials, that what will be if I want to make in a bulk scale, a lot of for different application, but then, invariably humans and others will be exposed to them. And then the other question that generally people ask to me or others similar when we present this kind of work, that how large scale can you make them? How much large scale? The question is, the response is, so far what I have shown are all scalable. The techniques that I have shown are actually industry compatible. But then, of course, more research needs to be done, that when we scale them up, whether the properties also scale. I can scale the volume of production. Whether the properties also scale up that way, those things are need to be looked into. Well, our group has got a couple of awards and recognition. The students have got recently award for their work. Our lab, please visit us if you're wherever you are. I'm sure after the pandemic gets over, you must be visiting Chennai, IIT Madras. Please drop in. I'd be very happy if you liked our work. I'll be very happy to show you around. Lot of people, although I have talked for about now 55 minutes, but this work would not have been possible with active help from my PhD student, postdocs, interns, funding agencies, of course, who actually keeps all the money, keep the money flowing. I would thank our head of the departments at different time, including our current head of the department, Professor Arul. There are several colleagues in the department with whom I have actively collaborated. We have seen the results. Collaborators from the other department within IIT Madras, national level collaborators, and then there are a few international collaborators. Last but not the least, thanks to IIT Madras Alumni Association for giving me this opportunity to reach out to you. And I can always be reached through email. I have a bad habit of checking email every few minutes, except a few hours in night. You can reach me at somnath@iitm.ac.in. Thank you so much. Have a great day or great evening.
Thanks a lot, sir, for a very wonderful presentation. So we have a couple of questions in the chat box, so I'll read them out for you. So the first one is, out of all the vertically aligned nanomaterials, 1D or 2D, which would you suggest if one is interested in EUV or X-ray regime to construct polarimetric devices?
So can you please read out again, once again?
Yeah. So
what application?
So the application is to use these materials for polarimetric devices in the EUV or X-ray regime.
X-ray regime.
Yeah.
Okay. So, well, I do not have a direct answer immediately, because we have looked at their light responsiveness, how they work under sunlight, what is their response under visible light, particularly visible light. But these are also responsive to electromagnetic radiation of various wavelengths. X-ray, if I can say, well, we do use X-ray for characterization, as I have shown X-ray diffraction, to actually know that how this structure, whether the crystalline structure has actually created or not, those kind of things. But we can discuss it further. I mean, you can reach out to me, the person who has actually asked the question. I request you to reach out to me through email. We can discuss further to understand the exact thing. So as I said, as of now, our focus is to see the light response, or in a more practical manner, solar energy application. That's what.
Okay. So the next question is how to pick that single nano rod from a bunch of rods.
Beautiful question. Yeah, I was expecting that. In fact, we have done this. You know, the last few slides, you would have seen that we have two electrodes or pad, as you cannot see the electrodes, and you have seen like two river banks. Okay, I've just unshared it. Okay, anyway, I think you can recall two river banks, two banks, and then you would have seen the bridge. That was our nanotube or nanorod. Where what we do is that simply we scratch it out, like using a scalpel blade, surgeon's blade. We scratch it out. We put it in high purity alcohol, and then we disperse this. We take that alcohol in a micropipette with alcohol with the dispersion of this nanorod, and we put it under microscope, under the electrodes, and we actually try to isolate them under the microscope, under the electron microscope. It's not very difficult. Well, it cannot be probably done at home, since we cannot see them even using a light microscope. But light microscope with high resolution, we can see them. So it is not a day-to-day thing at home, I will say, but in a lab we do it. It's now very standard process in microelectronic fabrication.
Got it. Yeah. Then a follow-up to this is, and that nanorod has single pore. So what about multiple pores? Can we grow it like that? Multiple pores. Can we grow it like that?
Yeah, multiple pores means, so then what I can tell that we see when a particular one nanorod grows or nanotube grows, it has a single hole. Yes, there are certain chemistry which allow to grow one side of the nanotube will have multiple, I had seen multi-leg, but then the other side will always have a single outlet. It's like multiple inlet, but single outlet. In case for a particular application, we need multiple holes or inlet and outlet both. Simply what we can do is that we can select a bunch of nanotubes together. That way we have the control to fabricate the nanotube in that way that a few nanotube in bunch we can pick up like a single strand, and we can use that. That we can.
Got it. Then the question is, can we use PLD to grow that kind of nanorods?
PLD, pulsed laser deposition. So the nanorods which are grown here are actually all by chemical technique. It's true. Yeah, except that we used the sputtering technique at the end, the bismuth ferrite. PLD, I haven't grown, but PLD is of course a very sophisticated technique. I would love to have a PLD. PLD allows me to grow single crystal layer, epitaxial layer. In fact, we are trying, we will get, along with collaborator Professor Murugavel, we will get one. And Professor Santosh, all are involved. So what my idea would be to first have a layer or a few islands, which I will call as the nucleation sites of this material. Then have that in a PLD chamber and have the material get deposited preferentially on those spots or on those prefabricated islands. So it gets what we call a seed layer. It already, when the material comes in a PLD chamber to be deposited on a substrate. It already says, oh, there is a seat already for me. So once there is a known thing already sitting, the material will try to go and sit on top of that. So that way, probably we can grow. I haven't worked on PLD as such, but from my basic idea of thin film growth, I can predict that, yes, it can be attempted. It should not be very difficult.
Understood, sir. And sir, one last question. So what was your motivation for using graphene to coat the TiO2 nanorods?
Excellent question. So I will tell you a story. The story I will tell, there is a technical motivation, there is a non-technical and non-scientific motivation. I joined IIT Madras in 2010. 2010 was the year when graphene got Nobel Prize, or Gaiman Novoselov got Nobel Prize. So everybody was very, it's a happening thing. Something got Nobel Prize. As a scientist, I would like, oh, that topic got Nobel Prize, I should work. No, I will get some quick funding, quick papers like that. On top of that, as I mentioned, Dr. Manu Jaiswal, my little younger colleague, who also joined, who actually worked in leading graphene lab, Singapore, he also joined in 2011, and he had expertise in graphene. So we teamed up immediately that let's see, kya hota hai? Let's see what happens if I am a TiO2 nanotube guy, you are a graphene guy. We try to see, let's cook up something, what happens? So it was purely a curiosity-driven thing, fueled by the atmosphere around graphene, Nobel Prize atmosphere. But the scientific motivation behind that, graphene itself is an excellent electron conductor. And TiO2 suffers from this charge recombination problem. So we want to wrap it with graphene so that the graphene can take out the photo-generated charges quickly, and I get a higher sunlight harvesting in TiO2. So that was both a scientific motivation and a non-scientific motivation.
Thank you, sir. And the final question, I think, is, but sir, I think this is a follow-up to the previous PLD question. So, but sir, it will be Volmer-Weber grow, isn't it, in PLD? So I don't
PLD, yeah, as I said, I am not very familiar with that. We are planning to do, yeah, I mean, if you have something already on a substrate, then of course the PLD, the entire process will be absolutely different from the chemical techniques that we are going. But what I wanted to mean that if I already have, suppose on the substrate I keep in the PLD chamber, then you have this pulse laser going and hitting the target material. I'm sure the person who has asked PLD knows that. And then we have the plume of material falling on the substrate. My point was, if I do not have anything on the substrate a priori, then a single layer, a beautiful single crystal layer, epitaxial or a polycrystalline layer might form. But if I already have some island growth, or what we call a seed layer, then probably I can get this rod type. It is my idea. I mean, I never tried. Of course, this will be much different than the chemical growth, but the basic crystal growth concept will be similar. That is my.
Understood, sir. So I think we've reached the end of our questions, sir. Thank you for a wonderful presentation, sir, and for taking the time to share the details of this fascinating research area. And sir, so mostly that's it from our side. So
thank you so much.
We were very much excited to know about your research. And yeah,
thank you so much for all the audience who are present here. I hope you liked it. If you have more questions, you can reach out to me. I've shown somnath@iitm.ac.in. Anytime we can collaborate. We can we can work further if you're interested. And as I said, whenever you are visiting here, please do come in. We'll be very happy to share with you our excitement, our lab area and all. Be safe and stay healthy. Bye-bye.
Bye, sir.